Welcome to the second review lecture. Since the course consists of a lot of information, a lot of heavy information, I thought of breaking up the review into shorter lectures. That would be much easier for you when you want to look at the overall course just by looking at the review part of it. In this lecture, we would look at momentum flux. Reasonably in brief, we had spent a good amount of time on momentum flux. In the previous review lecture, we looked at mass conservation as well as mass flux. And I think before I begin this, I should also tell you some aspects of learning. I think you need to take that as a part of, you need to internalize that, and only then would you be able to see this course in proper light. So, let me just quickly go to that. We talked about learning aspects, and in a class different people have different skills and so on and so forth. We said that the Gaussian distribution is a typical representation in number of students versus relevant abilities. And this typically holds when the number of students in a class is 15, 20 or more. I've seen this happen time and again. The exact nature of the curve could be slightly different, but the Gaussian is a very good first approximation. This we all understand in a class which is a completely heterogeneous class such as this. This I am sure would hold. The relevant abilities include knowledge in a domain and high learning skills. Higher learning skills include analysis, application, synthesis, and maybe I think this covers most of it, and affective skills and psychomotor skills also. As and when needed, we could restrict our view to analysis, application, synthesis as high learning in this for this particular term, relevant abilities, as well as knowledge in the domain. The most students would be somewhere here as indicated by this graph itself. However, there are quite a few who would be here and quite a few who would be here. Okay. The fraction is small, but when the numbers are large, the actual numbers could be large. These people may feel bored with the repetitions because they have gotten it quickly. These people would need repeated exposures. Just look at the same material a few more times to get there. Again, this is entirely course dependent, very specific thing. This distribution may be the person who is here for this particular course may be here or will be here for something else altogether. I could be somewhere here for this course at this stage, whereas probably for singing and dancing I could be somewhere here. Okay. So, it's not a judgment on the student, it's just that it's just a statement of fact, and statement of fact more from the point of view of improving the learning, what needs to be done to improve, so that we all get to a certain stage. That's the whole idea in giving you this. And of course, I said that most learning strategies address students who are in the average domain here, the average students as I call them. Whereas I could also address these people, may not be to the extent that I can do in a regular class, but I have attempted some of these things here. There have been a lot of strategies that have been woven into this course. It is just not giving you information alone. The way it is given, the way problems are placed, the way the problems are solved, and so on and so forth, all go into improving the learning of students, so that whatever the distribution is or was at the beginning of the course becomes this at the end of the course. That's the whole idea, or this is the central theme, central basis on which I work. I have no other interest, just to move the average to the right as well as narrow the distribution. I think this needs to be kept in mind, so that the way you approach the course, if you find a little uncomfortable, just redo that. If you are comfortable, if you are too comfortable with it, just look for bigger challenges. It's a class, and we need to take the entire class together. I teach at the average level, and so they should be fine, which is most of the students. Okay. Now let's look at momentum flux aspects. We talked about fluids, and we looked at a case where a thin layer of fluid is placed between two parallel plates, semi-infinite, and then the lower plate is moved with a velocity very low velocity in the x direction, positive x direction. The upper plate is held constant, and with this scenario we could introduce the concept of shear stress, because the layer that is closest to the lower plate will move with the velocity of the plate, and that influences the layer above it, and that will start moving with a slightly slower velocity. The second layer influences the third layer through the shear stress, and that will start moving at a slightly slower velocity compared to the second, and so on and so forth, to result in this kind of a linear velocity profile. We also talked about our terminology here. Tau yx, the first subscript is for the direction of action for first approximation. The second is for the direction of motion. This is for initial understanding. Later it gets a little complex, as you already know. And this is the shear stress. Then we saw how the shear stress can be interpreted as the rate of momentum change per unit area, or the momentum flux. And then we started looking at some properties of fluids themselves. We said that there are a large class of substances which follow the Newton's law of viscosity. Newton's law of viscosity is a relationship between shear stress and the velocity gradient, or the shear strain as it is called. And it's a linear relationship between the two, with the line passing through the origin, and such a fluid is called a Newtonian fluid. And also this is a constitutive relationship similar to the Fick's first law. Flux, the momentum flux, is directly proportional to a velocity gradient, and the constant of proportionality happens to be the viscosity here. That's what we said. Viscosity is the fundamental material property, and you could back out the units for viscosity as ml minus 1, T minus 1, using the dimensions of these various other terms here. So this is our Newtonian fluid in the relationship between, in the rheological characterization, which is a relationship between the shear stress and the shear rate. Newtonian fluid, and then we saw another kind of fluid, a Bingham plastic, which needs a particular threshold shear stress to manifest a velocity gradient, in other words, to move. When it moves, there is a velocity gradient. That will happen only when a certain threshold shear stress is reached, tau naught. Okay, that is called the Bingham plastic, and this is the expression for the Bingham plastic. Tau yx equals tau naught minus mu dv dy dvx dy, if tau yx is greater than tau naught, and it is 0, the dvx dy is 0 if the shear stress is less than a threshold shear stress. So this is the mathematical representation of a rheological representation of the Bingham plastic in a mathematical form. Then we looked at the other types of fluids that are there. One is the pseudoplastic fluid, the other one is the dilatant fluid. The pseudoplastic fluid and the dilatant fluids can be described by using a power law. Their rheological relationship is given by a power law. That is something like this: tau yx equals minus m dvx dy raised to the power of n minus 1. All these can be considered together, times, of course, the velocity gradient dvx dy. Of course, you could take the minus along with this, dvx dy. Okay. Here this term m dvx dy raised to the power of n minus 1 is called the apparent viscosity, and if n equals 1, this term disappears and m equals mu, the Newtonian viscosity. If n is less than 1, then you get the pseudoplastic behavior. If n is greater than 1, you get the shear thickening or the dilatant behavior. So, these are the kind of fluids. In addition, you have something called, those are some of the videos. In addition, there are fluids where the shear stress depends on the shear rate as well as the strain, and the Maxwell's model that is given here, tau x plus mu by g dou t of tau x equals mu times minus dvx dy. This is the one that describes a viscoelastic fluid. Okay. This is called the viscoelastic fluid. Examples of synovial fluid and hyaluronic acid and so on and so forth, mucus. Okay. Then of course, we talked a little bit about blood being a very complex fluid. Also interestingly, if the shear rate is less than 20 dynes per centimeter, if the shear stress is less than 20, shear rate is less than 20 second inverse, then it behaves as a complex fluid. If it is greater than 100 second inverse, then a Newtonian fluid is a very good approximation to the behavior of blood. Okay, and then a video is given. Also, we said that the type of flow is important for the characterization or for our understanding of the fluid behavior, and then design and operation and so on and so forth. So, there are two major types of fluids. One is called laminar, which is flow in layers depending on the geometry of the system. The layers could be either flat layers or they could be cylindrical layers as in a tube, or it could depend on the geometry of flow. Essentially layers, or it could be turbulent when pockets of fluid tumble over each other during the flow. Okay. So, these are the two types of flows. We looked predominantly at laminar because it lends itself to a certain understanding. Turbulent flow, we saw how to approach it, and then we had to resort to not so rigorous approach to make use of or to attempt to design with turbulent flow and so on and so forth. Let me briefly get there. Of course, we talked about the Reynolds number, which is nothing but the ratio of rho v d by mu, rho and mu density and viscosity of the fluid, velocity of flow, and the diameter of or a characteristic dimension. It could be the diameter of the tube, the distance from the starting point for a plate, whatever it could be. Okay. This can also be interpreted as the ratio of inertial forces to viscous forces in a fluid. Okay. And only in a pipe flow, if the Reynolds number is less than 2100, you will have laminar flow. If the Reynolds number is between 2100 and 4000, we are not too sure, we call it the transition regime. If it is greater than 4000, then it is in turbulent flow. Okay. This has been found. Okay. Then we started looking at solving problems. Essentially, we are interested in getting velocity profiles and shear stress profiles. That is the big insight that we get from these analysis, and they are very helpful, useful for design and operation. There are two major approaches, as we have seen earlier in the case of mass flux. One is balances over a representative shell, or shell momentum balances in this case. The second one is application of the conservation equation, or in this case application of the equation of motion, which is the equation of the conservation of momentum, Newton's second law, whichever way you want to call it. So, when we applied the shell balances, it gave us, as expected, a very good physical feel. We could visualize the forces, how they are related to each other, and so on and so forth. Only thing is that it is cumbersome. The effort becomes the approach becomes cumbersome, especially when we have the cylindrical coordinate system and the spherical coordinate system. Okay. So, this is the momentum balance equation, a useful form of that, rate of momentum out of the system minus rate of momentum into the system plus the rate of momentum accumulation in the system equals the sum of forces acting on the system. Okay. And this we had we had applied to the shell, in this case a cuboidal shell, and we said that the this was shell balances, right? Yeah, it's cuboidal shell, but this was let me see which flow I applied it to. Yeah, it was flow over a flat inclined plate, Bostwick viscometer, right? We said that there are two major means by which you can account for momentum. One is the molecular means, the other one is convection. Okay, there is a bulk flow, there is a velocity, there is a mass associated with it, there is a momentum. And in the case of molecular means, we have already seen that the shear stress is nothing but the momentum rate, momentum flux. So there are two different contributions, major contributions. And we looked at the flow over a flat plate, well developed flow over a flat plate. The thickness of the fluid layer is a small delta. This is the direction of gravity, this is the direction of flow z, and there would be changes in velocity and shear stress in the x direction, the direction that corresponds to the thickness of the liquid layer. Then we went systematically, wrote down the terms, molecular mechanism terms, area times the shear stress, that should give us the momentum rate. And for convection, we had used the rho Vx as the momentum flux times the corresponding area, that would give us the momentum rate. However, we combined it slightly differently for it to make some sense later. So, we wrote it like this, and I had shown you that you get the this is momentum mLT, mL by T is momentum, mass into velocity, momentum rate, and momentum rate, this is, you take all these three together, it is momentum flux. Therefore, you need to multiply it by the area to get your momentum rate. So, then we looked at a free body diagram to work out the forces that are active. Then in this situation, we saw that the pressure forces will cancel when if we consider the thickness of the film to be very small, right? And so the only main force that acts in the direction of motion is a component of the gravity. So this is the only force that is relevant here for our situation. Then we wrote the balance and then got an expression for the shear stress as this. The complete expression was after we got the boundary after we got the constant of integration, that was tau x z equals rho g x cos beta, right. And then we said that if we also are interested in the velocity profiles, we have the shear stress profile. Therefore, you need a relationship between the shear stress profile, shear stress and velocity to get the velocity profiles. And that relationship is directly the Newton's law of viscosity, because we had considered a Newtonian fluid. And when we substituted that, we got an expression for the velocity profile. Okay. The velocity profile was a parabolic velocity profile, and then we backed out the maximum velocity as well as the average velocity and the flow rate, right. So, that was through shell momentum balances. And then in the next chapter or the next lecture, next sub-chapter, we derived the equation of motion. We derived the equation of motion by considering a generic situation, such as this, the same way that we did for mass balances or the equation of continuity. And then these are the direction of flows, the flow in the x direction, entry exit, the flow in the y direction, entry exit, and the flow in the z direction, entry exit. So, a very general situation. And then we wrote the contributions of momentum flux due to convection and molecular aspects in terms of the variables that we can measure, we are comfortable with, and so on and so forth. Then we did this, we saw that this term, the convective term for the momentum flux, has 9 different components. So, this is the x momentum rate, y momentum rate, z momentum rate. The x momentum rate itself has 3 components, the y momentum rate has 3 other components, and so on. Similarly, we looked at the momentum rate by molecular aspects. For that, we looked at the force that causes the surface force that causes the shear stress or the momentum rate, momentum flux, sorry. The components we saw, then if you divide by the area, we got the stresses, both normal stresses and shear stresses. Also, it was pointed out that the normal stress is a different quantity, different physical quantity. It's different from pressure, although they could be added for many calculations and so on and so forth. They are 2 different physical quantities. Then after a balance and by a lot of simplification using various different physical relationships such as equation of continuity as well as mathematical representations, we got this equation which says dou t of rho v, which is rate of increase in momentum per unit volume, equals minus del dot rho v v, which is rate of gain in momentum by convection per unit volume. This is rate of gain in momentum by viscous effects per unit volume, del dot tau. This was pressure force on the element per unit volume. This is the gravitational force on the element per unit volume. Okay. All this we saw. Then I think we looked at these terms which are different, rho v v and tau, which are actually second order tensors, which have 9 components. We saw some aspects of those, and then if you want to know the tensor algebra, we were directed to the appendix of the textbook. So, this is the dyadic product, the product between 2 vectors, okay, which is very different from either a dot product or a cross product that you are familiar with. This is a dyadic product which results in 9 components. Then we went through simplifications, as I mentioned, to arrive at the form of an equation that is more useful. Rho substantial derivative d dt of v equals minus del dot t, which is viscous forces on the element per unit volume. The left hand side can be interpreted as mass per unit volume times acceleration, okay. And this is minus del p, which is pressure force on the element per unit volume, and plus rho g, which is the gravitational force on the element per unit volume. So, this has been written in its various components in various coordinate systems, and all those are available as tables 3.4.1 to 3. You are asked to make a copy of those tables and keep it for ready reference, because as you saw, we refer to them very often whenever we are looking at velocity profiles, shear stress profiles, and so on and so forth. We need to refer to them very often, because essentially we have brought down the equation of motion, or that principle, the momentum balance principle, onto these equations, reasonably general in applicability, and all we need to do is go to the table, pick up the relevant equation, cancel the irrelevant terms, and you directly have a governing equation well grounded in the physics principles that would lead to a robust analysis. So, that is the advantage here. So, I had shown you how this can be applied to the case that we have already seen, which is the flow over a flat plate, to get relationships in a useful fashion, without expending too much effort. You could do that, which may not be the case if you use shell balances. Then we looked at the simplifications for a Newtonian fluid in laminar flow, and that's when we get to a Navier-Stokes equation if rho and mu are constant. Also, if the shear effects are also not important, then you get to the Euler equation. Right? Navier-Stokes equation is very popular, and that's a special case of the momentum balance equation. Then I showed you the various different applications of this equation of motion, very relevant, highly useful situations we saw. Yeah, this is what I showed earlier. Yeah, this I had already discussed, falling film. We had looked at flow in a cylindrical pipe, got very useful relationships. This flow in a cylindrical pipe, you could apply it to a wide range of situations, right from flows in the body to flows in the industry and so on and so forth. We used the equation of motion to come up with the fact that the pressure across a cross section is the same. The pressure across two different cross sections could be different. The pressure across a particular cross section is the same. It doesn't vary with the radius or with your angle. And then we got the velocity profile, I think, first. Yes, Vz equals delta p minus delta p r squared by 4 mu L 1 minus r by r squared. Okay. Thus, the typical parabolic velocity profile in laminar flow in a pipe, we got an expression for that. So, this is the laminar parabolic velocity profile in laminar flow that I have shown. And then we looked at the shear stress profile, which turned out to be a linear shear stress profile. Okay. It's a highly relevant. And then I think that's good enough for this. I think we of course backed out the expression for maximum velocity, flow rate, the average velocity and so on, and also looked at the Hagen-Poiseuille equation, which relates pressure drop and volumetric flow rate. We said that if you double the diameter, then the flow rate increases 16-fold and so on. Okay. Those were the salient points there. Then there were applications to capillary flow, cuvette flow, which is flow between two cylinders in this case, the example of cuvette flow. Then you were introduced to non-dimensional analysis, dimensional analysis, which involves non-dimensional numbers. There we saw that even without knowing much about the system, just by doing an analysis on the dimensions of the system using the Buckingham Pi theorem and a certain procedure that seems to work, we can get very good insights of the kind of relationship between variables, even if we know nothing about the system. We have not done any experiments and so on and so forth. Then probably a few experiments can be done to fix the constants and so on and so forth. Then we got into unsteady state flow, where once you bring in the unsteady state dou t term, then it just complicates the mathematics quite a bit. Okay. And again, to emphasize, this is not a course that tests your proficiency in mathematics. You need to know how to solve something, that's it. How complex it is and so on and so forth, we are not really bothered at this undergraduate level. Okay. They are of course important, that can probably be taken up at the graduate level. Therefore, the idea here is to show you that there are solutions that exist. We don't expect you to become experts in the kind of solutions, kind of heavily involved mathematical solutions in this course. Basal level, yes, that is based on your the information that you picked up in the engineering mathematics courses, up to the solution solving differential equations, knowing some methods for solving partial differential equations, some methods for solving ordinary differential equations, and so on and so forth. Any of the other things are of course specialized, and that was given to you as information. Okay. The expertise in that is not expected as a deliverable in this course at all. Then we spent a good amount of time, or before even that, I should say, an example of unsteady state flow is pulsatile flow. We saw how to handle that, and then we also saw how to handle turbulent flow. Probably we should spend a little bit of time there in the review. We said that the principles, the physical principles, should be applicable to the flow irrespective of the type of flow, okay, because those are physical realities. Therefore, the equation of motion, equation of continuity would certainly be applicable. And we said if you can express your velocity as a sum of an average component and a fluctuating component, the pressure as the sum of an average component and a fluctuating component, the same equations that we had can be used. They reduce to simpler forms, and we could use the simpler forms if it becomes necessary to use them. Then we slowly veered off into an empirical way of approaching turbulent flow. Let me just get there. So once you did the time smoothing, this becomes your equation of motion, which is essentially the same, except that you're using, essentially the same as the laminar case, except that you're using the average components of the velocities here. The time smooth equation of motion is almost the same, except for this additional term with Reynolds stresses. Then, yeah, so this is what I was trying to say. Vi by Vi bar, P by P bar, and tau ij by a laminar component and a turbulent component, the shear stress, a laminar component and a turbulent component. Then you could use the same equations as earlier. The velocity profiles we saw, we said that this is, although in form it is the same as for a Newtonian fluid in laminar flow and so on and so forth. You could use that for turbulent flow also, with the recognition that this is not the molecular viscosity, right? That is what we said. Then we saw Diesler's empirical formulation. Okay. So far it was based on the fundamental equations, and now it's an empirical method. This is a useful method to get velocity profiles based on experiments, and therefore they are limited to the ranges over which they've been found to be applicable. The other ranges we don't have any confidence in applying them. Good. So then we got into the macroscopic aspects of fluid flow, of momentum balance, and so on and so forth. We looked at the engineering Bernoulli equation, although we didn't derive it in detail because of the reasons that I mentioned. We looked at the various applications of the engineering Bernoulli equation, and we said that if you can define a friction factor for each situation, then the friction factor approach can be taken to gain good insights also, and definitely use it for design and operation, right? So this was the engineering Bernoulli equation, just stated: delta P by rho plus delta V squared by 2 plus G delta Z plus frictional losses per unit mass plus shaft work per unit mass equals 0. And the main idea, the underlying theme for this part of the course was what are the friction factors for various situations. In this case, friction factor for flow through a straight horizontal pipe we got as 4f L by d V squared by 2 4f L by d V average squared by 2, and you could also write it in terms of the hydraulic diameter and thereby make it applicable to a non-circular cross section. Then we said, since this does not take into account the type of flow, this is applicable for laminar flow as well as to turbulent flow. The details would of course be different, but the form is certainly applicable. Then, this is the friction factor chart, the fanning friction factor chart. friction factor versus the Reynolds number. So this is 16 by NRE. This is, you'll have to read it from the chart, for various values of pipe roughness. Then we saw the application to different situations. One was stenosis in the artery, to get to a very interesting condition of the cavitation effects, when do they become important, and so on. Then we saw application to motion, relative motion between a solid and a liquid, then to packed beds, and so on and so forth. Okay. So, a large number of applications. For the exact expressions, please go back to your notes and take a look at them. I am trying to give you an overall picture. That is the reason why I am not showing you the exact equations, except when there has been, I felt a need for them. Okay. So, this being a review, I am not going through each and every single aspect of it. Please go through your notes and fill in the details whenever you need to. Okay. Forgetting is very normal, and that's the reason why we have textbook notes and so on and so forth. Right? Okay, I think we should need to stop here. We've been at it for quite a while. It's best to break it up. When we meet next, we'll do the next part of the review and probably one more and finish up with that. See you. Bye.